Hi, welcome. My name is Shenwei Zhang. I am an undergraduate student at Johns Hopkins University, affiliated with Malone Center for Engineering in Healthcare. Today, I'm going to introduce the framework of a smart surgical scheduling tool, an optimization model with integrated perioperative information input. Operating rooms are one of the main resources in hospitals, and any disruption in their workflow can have a cascade effect on the rest of the hospital operations. There has been a growing interest in optimizing OR utilization in hospital management. However, many of those work only consider a portion of the perioperative process, and one untouched area is designing a OR scheduling system that effectively improves the overall operational efficiency. The complexities in designing such a system come from various perioperative inputs. There are three types of inputs. The first one is the surgical features from patients' electronic health records, which give the OR schedulers the basic information of the case, patient, and procedure. The second input is the OR administrative rules, which put some constraints on surgeons using the OR in certain manner, and it is mainly reflected from the master block schedule. The third input is the post-operative capacity constraints, which involve downstream facilities such as PACU, ICU, and surgical bed. Our work focuses on systematically integrating all three inputs into the OR scheduling process to ensure a smooth patient flow. So first, I'm going to introduce the framework of this proposed Smart Surgical Scheduling Tool, aka SSST. The foundation of this tool is a OR scheduling model, which is formulated as a mixed integer program that schedules incoming surgical cases to certain OR and time slot in the scheduling period. This model takes input from three different modules, including master block schedule, incoming surgical case features, and daily surgical bed census focused. Noting that for these two modules, we created complementary predictive models that give more accurate estimation on some input parameters and will further optimize the case schedule. Then we use Groby solver to solve this model and output an optimized case schedule. We have several objectives defined here, and we achieve them through the multi-objective optimization model. After each scheduling iteration, the remaining OR capacity and surgical bed capacity are updated to reflect cases already scheduled and prepare parameters for the next model run. Further, we define some metrics to evaluate how good the schedule is. So let's first discuss the input modules on pre-operative information. The first input is the pre-specified OR information queried from master block schedule, including OR operating hours and OR in-block surgical service. Basically, the in-block surgical service tells us which OR on which day is scheduled for which OR service. It is encouraged but not required for the actual case schedule to follow the in-block surgical service. The second preoperative input is the surgical case features queried from hospital Epic data warehouse, which include case surgical service, case time window, patient class, and surgeon estimated case duration. One thing we observe from the data is that the surgeon's estimated case duration is usually not accurate, while this input is crucial to the OR scheduling model. So we are motivated to query more patient-related and procedure-related features and build a predictive model for this input. We trained the prediction model with 12 months historical surgical encounters. We developed two types of candidate models: all-inclusive model that trains on all available features, and service-specific model that trains individual models for each OR service. For each model type, we apply three machine learning algorithms: random forest, XG boosting, and linear regression. Then we test the candidate models on the test set and compare the result with surgeon's estimation. The evaluation metrics are R squared, mean absolute percent error, and the accuracy, which equals to 1 minus MAPE plus minus standard deviation. The conclusion is that service-specific models outperform better than all-inclusive models, and actually boosting slightly outperforms other algorithms. Then we select the deployable model for SSST from the service-specific models. For each OR service, select the algorithm that it has the best prediction accuracy. In this manner, we are able to improve prediction accuracy for 19 services out of 44 compared to surgeon's estimation. Next, we discuss the input modules on surgical census focus. Surgical inpatients are usually admitted to downstream surgical beds after surgery for several days of medical care before getting discharged. Therefore, the surgical census level puts reverse constraint on our schedule. So we are motivated to develop a predictive model that provides dynamic daily surgical census focus based on the current scheduled case volume. This focus is dynamically changing because after each scheduling iteration, the remaining daily surgical census capacity will be updated and become a constraint for the next iteration. Then, in order to predict the daily surgical census, we can decompose it to individual contributions. We can predict the individual patient's length of stay. And to predict the patient length of stay, we can predict patient discharge probability per day. This actually becomes a more specific problem, and it falls into the domain of survival analysis. Survival analysis is a time-to-event method, and in our problem setting, the event we would like to predict is patient being discharged from the hospital. The model can give a discharge probability per day, and y minus that probability is the probability of the patient contributing to the census. We train the model with historical elective surgeries and their length of stay. Two survival analysis models are generated, one using OR service as predictor and the other using OR procedure. The output of two models are two census contribution files for each service and procedure. As you can see in this table, for service cardiac surgery, the length of stay index range from 0 to 14, and the census contribution monotonically decreasing from 1 to 0. And the table for procedure muscle biopsy is similar. Later, we can match the incoming surgical case census contribution with its service or procedure, and after we determine the surgery date in the scheduling model, we can calculate its census contribution in the next 14 days. The further validation shows our procedure model performs better and is integrated as the census focus model in SSST. After going through all the input modules in the framework, I'm going to talk about the backbone of this tool, which is the OR scheduling model. The scheduling model is formulated as a multi-objective mixed integer program, which can schedule candidate cases to certain day and room using binary decision variables. We run the model daily, and the scheduling period is 1 week from the model run date. Since we do not schedule cases during weekend, the actual scheduling period is 5 days. After each iteration, some cases are scheduled and some are not. Scheduled cases are posted and removed from the candidate case list, while the unscheduled ones remain for the next iteration. Also, the remaining capacity parameters are updated based on the scheduled case volume. The model is written into Python, and we use Groby Python interface to solve. There are 4 optimization features considered in this model: reduce overall and block utilization mismatch, consider downstream surgical bed capacity, reduce OR opening cost, and prioritize urgent cases. We provide the formulation of each model constraints in this slide. The input parameters are surgical case J, scheduling date K, ORR, OR operating hours HKR, last day of the case window NJ, binary patient class CJ equals 1 if inpatient equals 0 if outpatient, daily surgical bed capacity bed KI, predicted case duration, TJ, and remaining case time window, RJ. There are two variables involved. One binary decision variable, xjkr, decide whether schedule case J on date Ki in ORR. One auxiliary variable calculates overutilized hours in each OR, B prime KR. The first three constraints control case scheduling. The first one ensures case scheduled at most once. The second one ensures case cannot be scheduled after its time window. And the third one ensures we must schedule the case in this iteration if there's no remaining time window. The fourth constraint controls not exceeding surgical bed capacity. And the fifth constraint controls the overutilization limit. We then provide the formulation of each modal objective. Some additional parameters are binary in-block service match, SJKR, which match the service type of case J to the in-block service type of ORR on date Ki. Another auxiliary variable is the underutilized hours, which is just the opposite formulation of overutilized hours. The first two objectives minimize the total under and overutilization hours. The third objective minimizes the outblock utilization hours. The fourth objective minimizes the sum of scheduled case remaining time window. And the fifth objective minimizes the total number of open ORs. Since all five objectives have been normalized and the denominators are all constants, the overall objective function is just a linear combination of them with p-noti factor M1 to M5. As we discuss the optimization model formulation, the last module is to evaluate the output case schedule. We evaluate the output schedule through a 3-month OR scheduling simulation. We collect all the historical elective cases operated in one OR site with 6 ORs from January 2019 to March 2019. Then we run the proposed SSST on this case set and output a new schedule in the same period. We first compare the proposed schedule with the original schedule on the average elective utilization rate in percentage, which is the average daily total utilization. We present two figures here, one using estimated case duration and the other using actual duration for the measurement. Although our scheduling model utilizes the estimated duration as the input parameter, the two figures show the final utilization rates are similar, which indicate our previous case duration focus is relatively accurate. In both figures, the highlight is that the proposed schedule increased the average elective utilization by around 8%. Then we compare two pairs of metrics. One pair is out-block utilization versus in-block utilization. The highlight is that the proposed schedule has lower average out-block utilization and higher in-block utilization, which indicates that the proposed one follows the master block schedule better and reduces the block utilization mismatch. Another pair of metrics are overutilization versus underutilization. The highlight is the proposed schedule almost have no overutilization and lower underutilization, which indicates the proposed one managed OR operating hours better and reduced the overall utilization mismatch. Then an additional metric is to compare the surgical census utilization in 3 months. The cap is set as 40 beds. Both schedules never go over the cap, while the proposed one has a lower daily census standard deviation, which can help smooth the patient flow in downstream resources. To conclude, the SSST we propose demonstrates a comprehensive perioperative framework. It is embedded with predictive models, which give accurate input parameter estimation and bed capacity forecast. It is automated by replacing traditional manual scheduling work. It is highly scalable by introducing more capacity constraints into the framework. It is portable to other hospitals with their medical record database. By deploying this tool, Our expectations are to save our operational costs, to ensure smooth patient flow in perioperative process, and to improve the patient satisfaction during hospitalization. Thank you for listening, and thank you to Informs for this opportunity to present my work.